Hello, everyone, and welcome to today's event, Beyond Denial and Doomism, What Science Actually Tells Us About the Impacts of Global Warming. I'm Jim Street, co-founder of the Financial Industry Climate Leadership Network, and I'm delighted to share the virtual stage today with three very distinguished panelists who will help us deepen our understanding of climate change and its consequences. So just a couple of housekeeping notes before we begin. Right now, all attendees should be on listen only, but we'll be able to take some questions from the audience towards the end of the event. Also, please keep in mind this event is being recorded. We would have liked to have an event with an in-person component that would allow for more interaction between the audience members, but unfortunately, circumstances didn't permit that this time around. However, the chat is open. If people would like to introduce themselves, then please feel free to do so. And bear in mind, there should be a way to save the chat on your personal device. Your personal device, if you would like to do so. Our goal here is to provide a resource for people in the financial community who don't necessarily focus on climate change as part of their job, but who nevertheless would like to dig deeper into the issue and how it relates to the financial industry. I think most would agree that the industry has already come a long way in terms of how it's facing up to the challenge of climate change. Many institutions have already made net zero commitments, and ESG investing has been growing rapidly. But nevertheless, the industry continues to face criticism for funding fossil fuel related infrastructure and other projects and endeavors that contribute to climate pollution. So is that criticism justified? After all, the point has been made, and I think it's a valid one, that we can't just switch over to 100% clean energy overnight. So we'll need to continue to rely on fossil fuels, at least to some extent, during the transition. So the question becomes, what kinds of projects should the industry continue to fund, and for how long? And this question has relevance not just for the climate and the planet, which of course it does, but also for the financial health of the institutions providing that funding. Projects that are not consistent with the actions that need to be taken to avert the worst outcomes of climate change are more likely to be abandoned prematurely, potentially resulting in stranded assets and financial losses. So how should decision makers go about determining what kinds of activities should be supported and which should be avoided? And I think the answer has to start with the science. How quickly do we need to transition away from fossil fuels to avoid the worst outcomes? What are the consequences if we overshoot on emissions? What possible remedies are available and at what cost? What uncertainties exist in our understanding of climate change and its consequences, and how should those uncertainties impact the decision-making process? So to help us explore these questions, we are very fortunate to have with us three wonderful panelists. Dr. Jennifer Francis is a senior scientist and acting deputy director of the Woodwell Climate Research Center. Her research focuses on climate change in the Arctic and its potential impacts on global weather. Prior to joining Woodwell, Dr. Francis spent 24 years as a research professor at Rutgers, and she has authored several articles in Scientific American, one of which was just published yesterday. And she's appeared before Congress on 3 separate occasions. Welcome, Dr. Francis. Also with us is Dr. Adam Sobel, a professor of applied physics and applied mathematics and of earth and environmental sciences at Columbia University. His research focuses on extreme weather events with a particular interest in the tropics. He was featured in the 2012 NOVA documentary, Inside the Megastorm, about Hurricane Sandy, and later he published a book about that storm. He is a fellow of the American Meteorological Society and has received awards from that society and from the American Geophysical Union. Welcome, Dr. Sobel. And Dr. Gernot Wagner is a climate economist. His work focuses on climate policy and risks. He teaches climate economics and policy at NYU, where he is a clinical associate professor at the Department of Environmental Studies and also teaches at the Graduate School of Public Service. You may recognize his name because he writes the Risky Climate column for Bloomberg Green, and he's authored 4 books on climate policy. Prior to joining NYU, Dr. Wagner was a research associate and lecturer at Harvard, and he served as lead senior economist at the Environmental Defense Fund. Welcome, Dr. Wagner. So, Adam, let's begin with you. Your research focus is extreme weather, and to the untrained observer, it certainly seems like there's been an increase in the frequency and intensity of all sorts of extreme weather of late. Is that just because of the way the media is covering these events, or has there been an identifiable uptick? And is it possible to discern the fingerprint of climate change in those events?
Thanks, Jim. So this year in particular was extreme in every way. There's no question about it. Many events that were just about off the charts in severity, the Pacific Northwest heat wave, the floods in Germany and China and Tennessee, and fires out west, so many events. I think it's reasonable to, the science supports the view that some fraction of that is attributable to human-induced global warming. Some of it almost surely isn't. I don't think that the kind of year we had this year, it can't all be the global warming trend, because that would mean that, we would have expected to see lots of years like that in the recent past, which there have been some extreme years in the recent past, but not quite like this. And that every year like this, would be like this in the near future. And I don't think that's quite the case. So there's always natural variations on top of the human signal. But, so I think there was both this year. The long-term trends and what we know and understand about them varies a lot depending what kind of event we're talking about. So to take the ones that we're most confident about, heat waves are the simplest. In the simplest view, you would think that since the whole planet's getting warmer, if you define a heat wave as being warmer than some threshold temperature for some amount of time, then if everything else stays the same, but the whole planet's warmer, that you'd cross that threshold more often. And it's not quite that simple, but it's almost that simple. So we are seeing increased incidence of heat waves worldwide, and the climate models say that's what should happen. And it's not quite, but almost as simple as that. So things like the Portland heat event, which were that was really extreme. I don't think we can explain in all its detail so easily, but the fact that we're seeing more events like this is totally expected, and we can expect to continue, and human activities part of it. Extreme heavy rain events, a little less straightforward, but still there, it's a consequence of some pretty basic physics that in a warmer climate, you have more water vapor in the air, and the heavy rain events are good at squeezing that out. So, we see trends that there's more rain falling in heavy events in most places in the world where the data are good enough to judge it. The models also say that should happen. So at fires, fires are complicated in some ways, but in other ways they're not. If it's hotter, it dries out the soil and the wood that's on the ground, and the fuel for the fires more quickly, and makes fires more possible. It doesn't cause the fires, but it makes them worse when they happen. Then there are some that we know very little about. I mean, tornadoes, scientists are we don't have much to say yet about how those are changing with global warming. Hurricanes are somewhere in between. We know some things, but not some other important things. Like we don't know whether there should be more or fewer hurricanes in the future. It's pretty basic, but we don't know that. But we do see pretty clearly that they're producing more rain, and the winds are getting stronger. So, I think both things are true, in the sense that there is a human fingerprint on these events, but also every weather event has many causes, and human influence is only one of them in the background, and there's always lots of other proximate causes. So, you can never say global warming caused some event, full stop. It's never as simple as that, and if you see that in the media, it's just wrong. But on the other hand, with at least some kinds of events, the evidence has gotten a lot stronger that we can see the human influence.
Okay, thank you. Dr. Francis, let's turn to you now. Your research focus is the Arctic. I think it's fair to say that the Arctic is undergoing some profound changes right now. Why is that important for climate and weather in more temperate regions of the planet?
Right. Well, thank you, Jim, and thank you for inviting me to be here today. I do have some slides, if that's okay. if I can share my screen.
Sure. Yeah. Are you able to do that, or I might have to assign some permission?
It looks like it's letting me.
Okay, great.
Can you see that?
Yes, you can see it.
Okay. All right. Okay, so yes, Jim asked me to talk a little bit about some of my research involving the Arctic, what's going on up there, and really why it should matter to all of us. Obviously, in this picture, we're looking at a flooding event and the fact that the Arctic is warming so fast, which I will show you in a graphic, is causing the Greenland ice sheet to melt faster and glaciers to melt faster. And those two things contribute to sea level rise, which is causing the kind of coastal flooding you see in this picture and what we're concerned about in many coastal communities all around the globe. So that's just one reason. Another reason the Arctic is of interest to all of us really touches on what Adam has already been talking about, and that is the possible connection to some of these extreme weather events that he talked about. In fact, he mentioned this heat wave that occurred this past summer in the Pacific Northwest. You can see these temperature differences from normal shown in this plot here, where these red colors are just showing you unprecedented temperatures in the Pacific Northwest. But I also want you to notice that's not the only thing going on here. We've got the very hot temperatures there, but on either side, we actually have temperatures that are cooler than normal and warmer temperatures also in the east. And the reason is because this extreme event and many extreme events are related to these very convoluted patterns in the jet stream, shown in this graphic here by these blue jet stream words. And you can see that it's taking this very loopy pattern as it comes from the Pacific Ocean and up over the Pacific Northwest and then dipping back down into the middle of the country. When we see these very extremely convoluted jet stream patterns, almost always we see extreme weather events associated with it. So in this particular case, this big loop to the south has allowed a lot of the warm air from the southern latitudes to extend up into the tropics, up into the higher latitudes rather. And that's causing that heat wave that we were talking about. But also on the downstream side of the jet stream, you see these northerly winds, and that's what created the cooler than normal temperatures in the middle of the country. So one takeaway is that one type of extreme event is almost always associated with unusual weather conditions on either side. And just to touch on one other extreme event that happened this year, the very devastating cold snap that struck the southern Midwestern states of the United States this past February. These are showing the actual temperatures on a day in that February extreme cold wave where we saw temperatures below zero in Dallas, Texas, which at the time where it was colder in Dallas than it was in Alaska or Greenland or parts of those state areas at least. And this cold wave was extreme for many reasons. For one thing, of the extreme cold itself, but also the fact that it extended all the way down to the border with Mexico, and it lasted a very long time. And again, it was associated with a very unusual or extreme pattern of the jet stream, which is now shown by this storm track here, written in blue. And you can see that it's dipping way far south, allowing the Arctic air from the north to plunge all the way down into Texas and cause so much misery there. But it wasn't just a usual dip of the jet stream. We get these cold waves happening every year. We also had this sort of accentuating factor shown here by the pink polar vortex, which is suggesting that we had this extra cold air from the stratosphere, which is much higher up in the atmosphere than where the jet stream is. And every once in a while, the stratospheric polar vortex, which normally sits over the North Pole and it is a very circular pool of very cold air, surrounded by strong westerly winds that normally doesn't cause anybody any trouble, but every once in a while it gets disrupted and it can sometimes bring some very cold air farther south, typically down over the continents. And that's what happened in this particular extreme event. So the connection is to the Arctic potentially is that we are seeing these wavy patterns in the jet stream happening more often. We have scientific evidence suggesting that this is actually occurring. And we're also have some evidence now that these disruptions to the polar vortex are happening more often as well. And it could be connected to what's happening up in the Arctic. And so this map here is a little different from some of the global warming maps that you've seen before, in that it's showing how the temperature changes in different regions of the globe are happening relative to the global warming as a whole. And so where it's blue, it means that this area is warming slower than the global average, and where it's the red colors means that it's warming faster than the global average. So you can see very clearly that it's warming faster over land than over ocean generally, and the Arctic is warming much, much faster than anywhere else, about 4 times faster actually at this point. And so this difference in the warming in the Arctic, we think is having a lot of effects. And there's a lot of basic things that connect the Arctic to all of us down here at lower latitudes. But one thing I want to point out is that what's happening in the Arctic generally doesn't stay in the Arctic for a lot of different reasons. What we can see happening in association with the temperature changes up there is a loss of the ice cover over the Arctic Ocean. So the ice floating on the Arctic Ocean. So in the summer back in the 70s, it typically looked more like this map in the upper right corner here. Most of the Arctic Ocean was filled with ice. But as we get down here to the 2012, which was the year we had the least amount of sea ice ever recorded in the Arctic Ocean, these yellow and orange colors are showing you where there used to be ice. And the reason this is important, well, there's many reasons, but one of them is that the ice is, of course, very white. It reflects a lot of the sun's energy right back to outer space. And where we've lost this ice, we are now instead absorbing a lot more of the sun's energy into the climate system. So literally half of the sea ice has disappeared during the summer. And if you also take into account how the thickness of that ice has changed, we get about 75% of the volume of the sea ice has disappeared in only 40 years. This is just an incredibly rapid change to a very important part of the climate system. And this means by losing this ice, the Arctic the surface is darker now, the globe is actually darker now, and by absorbing all that extra heat in the place where sea ice and snow cover have disappeared, this is actually making global warming quite a bit stronger than it would be otherwise because of all that extra energy that's being absorbed. As I mentioned, the Greenland ice sheet is melting faster, that's accelerating sea level rise. Permafrost, which are the frozen soils in the high latitude land areas, is thawing faster, and when that permafrost thaws, it releases more carbon dioxide and methane into the atmosphere, which are both greenhouse gases, and that accelerates the warming of the globe. And as I touched on, we might be seeing a connection between this rapidly warming Arctic and the pattern of the jet stream. And just a quick kind of 101 on jet stream and why we think this might be a factor. If you could think about a layer of atmosphere that extends from wherever you are in the United States up to the Arctic, we know that the air is warmer down here than it is up in the Arctic, and warm air takes up more room than cold air does. So this layer is actually taller down south compared to the Arctic. And this creates a hill in the atmosphere. If you were sitting on top of this layer and looking northward, you would be looking down a hill. And the air on top of this layer wants to flow down that hill, creating a wind. And that wind then gets turned to the right because the Earth is spinning, and that's what creates the jet stream. It's the main reason for the jet stream. But because the Arctic is warming faster than elsewhere, the height of that layer, or the thickness of that layer is increasing faster in the Arctic than it is down here. And that is causing that hill to become less steep. There's less force driving those winds of the jet stream. And when we get a weaker jet stream as a result, it tends to be deflected more easily from its normally west to east path by things like mountain ranges and differences in temperature in oceans and things like that. So we generally expect a weaker jet to take these bigger north-south meanders, kind of like the ones I showed you in the very beginning, associated with those extreme events. And these waves are really important because not only does the jet stream separate the cold air to the north from the warm air to the south, but these waves also create the dynamics in the atmosphere that create the high pressure areas that we see on TV weather maps. In this part of the wave, this is typically what we've been seeing lately over the West Coast, where the wave has been parked off the coast and caused a lot of high pressure, leading to the long-term drought and heat waves that we've seen there. But this part of the wave over here is where we tend to see the stormy conditions. And we see the upward motions in the atmosphere causing low pressure areas that you might see on a TV weather map. But unfortunately, the real jet stream is nowhere near that simple. This is some real winds that have been animated by NASA's Science Visualization Studio. The red and yellow colors are showing you where the strongest winds are and where the jet stream is. And you can see that there's a lot of swirls and waves and different sizes that come and go. So you can imagine it's very difficult to measure what is changing in the jet stream, how it's changing, what's causing those changes. But we think that the Arctic warming so fast may be one of the factors that's leading to some of these extreme events happening more often, possibly causing the observed waviness in the jet stream increasing, and also possibly causing the stratospheric polar vortex to disrupt more often. So this is my last slide, just a look into the future and using sea ice as an example of the kinds of changes that have been happening and that we expect to happen in the future. So we're looking at the area of sea ice on the Arctic Ocean. As I mentioned, we've already lost half of the summer sea ice. This black line here is what's actually happened in the real world. And these gray lines here and the fuzzy lines here are simulations from climate models. So these very sophisticated computer models that we use to try to understand what happened in the past and also to try to project what the future holds. So you can see that the climate models did a pretty good job of simulating what the summer sea ice extent looked like in the past. And then we have these lines going into the future. And of course, the future really depends on us. So these are our choices. We've got what I would call the do nothing line here, which is the red line here. If we keep emitting greenhouse gases at the rate we're doing it and we're not able to curtail our emissions, then we're heading to a future in the not very far into the future where we're going to see a summer Arctic where the ice has virtually disappeared. But if we can get our act together and really figure out how to reduce our emissions of the greenhouse gases, use all the tools in our toolbox to try to extract carbon dioxide from the atmosphere, we might be able to keep ourselves on this green curve here, which preserves ice in the Arctic. It would keep the Arctic from warming too much more and perhaps also prevent many more extreme events from happening. But as you can see in the next couple of decades, it really doesn't matter what we do. We're going to be losing more ice, we're going to be seeing more extreme events, and it's really the future after 2050 or so where what we do today is going to matter for the future.
Okay, thanks for that, Jennifer. Let's pivot now to Gernot. You self-identify as a climate economist. Can you tell us what that means exactly? How can the impacts of climate change on the economy be predicted and quantified?
Sounds like this is a confessional now, a self-identified climate economist. So actually, let me start with sort of the very important and rapid change that frankly has happened when one self-identifies as a climate economist and what reactions one gets. So it wasn't long ago, decade or so ago, that the typical response was something along the lines of, wait, like pick your side, right? Like it can't be both. You're either one or the other, right? You're an economist, or you worry about birds and bees and the planet and so on. And that has changed. That first reaction has changed quite a bit. And by now, the first response is something along the lines of, oh, climate risk. You must work on identifying, pricing, figuring out how, or of course, sort of the solution side of things. What to do about it in some sense. Yeah, right. So the bread and butter of climate economics has always been, despite climate economists sort of formally being called oxymorons, has always been this process of pricing risk, quantifying, putting into dollars and cents, the sort of risks that Adam, Jennifer, many others are working on identifying on the physical science side, and then figuring out what it means in dollars and cents. And then, the flip side of this is the so what? Okay, cool. We now know that each ton of CO2 emitted today causes significant damage, translated into the cost of carbon per ton emitted. So what to do about it? What's the policy recommendations? How do we translate these things into policy? And it's the combination of these two, that frankly, makes this job interesting, and allows us to often have quite a bit of undue policy influence, if you will. There's a lot of self-reflection that needs to happen within climate economics, frankly. But that, of course, can then also, once one translates these ideas into workable solutions, policy recommendations, paths forward, can in fact be, in a good way, a very powerful way of looking at the world. So just to give you a sense of the parts of the bread and butter here, this sort of big metric out there, the world's most important figure nobody has ever heard of, or the result of the mother of all benefit cost analysis, sort of superlatives abound vis-a-vis this cost of carbon, social cost of carbon calculation, that is in many ways the bread and butter of climate economics, What's the present discounted value of the stream of future climate damages? That exercise is fraught with lots of uncertainties, with lots of questions, problems, and so on. But in a sense, it's precisely the sort of question or the sort of exercise that if it didn't yet exist, somebody would have to invent it, There are limits, there are problems, and so on and so forth. And frankly, there is the realization that at the end of the day, this ought to be all about the risks, the uncertainties, the stuff we don't quite yet know. Or put somewhat flippantly perhaps, but in sort of Don Rumsfeld, ex-defense secretary, late defense secretary language, It's not about the known knowns. It's not about the stuff we can quantify. It's about the known unknowns on the one hand and the unknown unknowns. And of course, the things we can quantify point to plenty of action, climate action that should have happened a long time ago. The things we can't yet identify, the risks, the uncertainties point to lots more action. It's not the stuff we know, it's the low probability, high impact events. It's the tails, the black swans, those sorts of things, the tipping points that ought to point to much, much more climate action, much more climate policy than we currently have in place.
Okay, thanks. That's actually a good segue, because my next round of questions was going to touch upon tipping points. But specifically, I wanted to focus on the Paris Accord and the goals of the Paris Accord, which are to limit warming to well below 2 degrees Celsius and 1.5 degrees if possible. And I was going to ask, what is the rationale behind those thresholds, and what happens if we go past them? And I'm sure some of that has to do with tipping points. But Adam, let's start with you. From the point of view of extreme weather, how should we expect the kinds of events you study to play out in the future in a 1.5 degree scenario, a 2 degree scenario, or if we go beyond that?
Right. So, I can't give precise numbers for any type of extreme event in those different scenarios, but I think, it's worth keeping in mind that the 2 degrees and these other thresholds are important because they give some, a sort of crux to the international negotiations. They give us targets that are meaningful, and I think, we have to take them seriously. But at the same time, from a physical science point of view, they're somewhat arbitrary. I mean, it's not as though there's no impacts before 1.5 or 2 degrees. We're at about a degree now, and there's already a lot of impacts we're seeing. And even if you go past 2 degrees, the 2 degree threshold sort of leads some people to say, well, then it's game over. We're dead at that point. That's not true either. And really, the reality is that every degree, every tenth of a degree matters. So whatever emissions reduction we can make are better than not making them. So the thresholds are important from some perspectives, but from other perspectives, it's possible to overinterpret them. In terms of what the extreme events will look like, I think that the sort of big picture thing I'd like people to know is that, first of all, as I was saying before, our certainty and our knowledge depends a lot on what kind of extreme events we're talking about. We know a lot more about some than others, and I think, maybe the single most important thing, especially from a financial industry point of view, is what Gernot just said. To put it in different words, it's a risk problem. Climate scientists have often framed it as a signal detection problem, meaning at what point can we say conclusively that what we're seeing is, couldn't have happened without human influence. But that's not how we make decisions in the real world. We have to make a decision, so we make it based on whatever evidence we have. And the uncertainties, the wider the uncertainties are, in some sense, the bigger our risk, because some of the uncertainty is on the bad side. But I think the other thing with terms of extreme events is that whether or not there are tipping points nearby in the climate system as a whole, and I think we're going to talk about that later, so I won't get into it. There are definitely tipping points in how some extreme events evolve, and especially in the impacts to them. There are some thresholds, where below that threshold it really isn't too bad, and above it, all of a sudden it's much worse. So some obvious example is with sea level rise. Sea level rise at some point, places are going to go completely underwater, but before that happens, sea level rise raises the risk of flooding events happening either due to storms, which cause storm surge, or extreme high tides. And and some places have seawalls, or they have whatever they have, but at some point, until some point, you're not underwater, and then after that you are. So we saw, for example, as you mentioned, I've spent a lot of time thinking about Hurricane Sandy, which was a huge disaster. The forecast for Hurricane Irene the year before was just about as the same, but the storm surge was a little less. It didn't get over the seawalls. It was no big deal for New York City anyway. It was bad upstate because of the rain, but whereas Sandy was awful. So it's just another example is human heat and humidity exposure. So above some point, there's some temperature range where a little warmer or a little cooler doesn't matter that much. And then when you get higher than that, it starts to affect people's performance, whether they're working or studying or doing anything else. And then when it gets to high enough thresholds of heat and humidity, you basically can't survive it anymore. And there are some climate projections that indicate that there in some parts of the world, especially South Asia and the Middle East, where we'll start reaching those thresholds at some point in this century, maybe not every day, but on some days, meaning that people basically can't live outside at that point. So, our impressions of how much these changes in extreme events, and by extension in the climate as a whole, matter from small changes, don't necessarily generalize to changes that are a little bit bigger. And that plus the uncertainties, I think, means that we have to really think about it in some counterintuitive ways. We have to look at the real numbers and what the real impacts are, and not generalize too quickly from our own experience.
Okay, thanks. So yeah, clearly there are temperature thresholds that if we cross them, then we start to, maybe non-linearly increase the cost, just because, as you said, of overtopping seawalls or reaching temperature thresholds that are extremely harmful for human health. But my impression is that there are also risks that we sort of lose control. We lose our ability to that climate change at some point takes on a life of its own, and we get to a point where if we cut emissions, we no longer have the ability to slow it down or to limit the increase. And Jennifer, you mentioned Arctic permafrost thaw as being one potential feedback loop or tipping point that could be triggered at some point. I also think about destabilizing ice sheets, that if we get to a certain temperature threshold, that we would lose, it doesn't matter how much you warm past that, you're going to lose that entire ice sheet, whether you freeze temperatures there or continue increasing. So I know a couple of those at least are associated with the Arctic. Jennifer, do you have any thoughts about which are the tipping points that you're most concerned about, and how close we are to triggering those?
Yeah, so generally I would say that the physical climate system doesn't have very many tipping points in it, in the definition that you fall off a cliff and you just can't get back up that cliff. I think of it more as kind of a staircase, where every step you go down the staircase, it gets that much harder to get back where you were. In the case of permafrost, there is a point in a local area where you thaw all the frozen soil that's in a location. If you thaw all that soil, it's going to take a very long time to refreeze that soil if you are in fact able to cool the climate system. So it's not a question of never being able to get that permafrost back, but it would take a really long time. And I think the same is true with the Greenland ice sheet. If we can maintain the Earth's temperature and even perhaps go back in kind of a cooling situation, we may not lose. There may not be a point where we lose the whole ice sheet. Again, I think it's just a question of degree. How far down the staircase do we get? That said, I think there are tipping points that are very concerning that have to do with the living part of the system. We've talked about humans, but there are a lot of other ones that affect other species that are living in the Arctic and elsewhere, where the conditions just become so extreme that that particular species just can't survive there anymore. That could be, an animal in the ocean. Take our coral reefs, which are dying at a very rapid rate. We've lost a couple of species just this past year we heard about that completely went extinct. You can imagine a species of animal living on a mountain, and as it gets warmer, they kind of go higher and higher in elevation, and eventually they get to the top and there's just nowhere left to go. But it's not just the wildlife, it's also agriculture. We just maybe can't grow certain crops in the places where we've been growing them anymore. And that could change whole cultures that depend on that particular crop. And then, potentially there's, getting back to the physical climate system again, there's been a lot of research just lately about the large scale ocean currents, especially in the Atlantic Ocean, and the fact that it appears that large scale ocean circulation in the Atlantic may be slowing down. We know that it has stopped in the past, looking way back in time. So there's a question about whether that could potentially be some kind of a tipping point in the system, but I don't think we know enough about it yet to be able to really put numbers on that, or timing, or probability, but there are some very worrisome signs coming out in the research about it in fact slowing down, and is probably also something connected to the Arctic, which we could talk about later.
Okay, thanks. So Gernot, you mentioned the known unknowns and the unknown unknowns, and that those are really, kind of those tail events when you look at them in probability weighted net present value are really, have an outsized impact on the models that you use or the frameworks that you use for the cost of climate change. So can you elaborate on that a little bit more? I mean, when you look at the social cost of carbon, how much of that comes from things that we know are relatively certain, impacts that are going to happen, certain amount of sea level rise for certain temperature increase and so on, and how much comes from this idea that, that we could reach these thresholds where things go a little bit nonlinear?
54% and 46. So, so here is sort of a slight detour in trying to answer this question, but environmental economics, climate economics, sort of the bread and butter of climate economics, for the longest time has been, sort of these benefit cost analyses, right? Calculating what we know, what we don't know, translate, and sort of the, standard analyst type work that, frankly, as a climate economist, I do it for climate, right? If I were in the employ of a financial enterprise, I would be doing the exact same thing, project evaluation, right, essentially. Now, the problem with sort of the standard view, the way we've been doing this as a discipline, is we've been doing it the same way for about 3 decades. Meanwhile, financial economics has moved on. And when I say that, so I'll throw out a few technical terms here now, so stop me if you want to explain any of these, but sort of with the financial audience, I think many of these sort of would be familiar. Sort of the, it's not just the average return, right, the alpha that matters, it's the risk, it's the beta that matters. And sort of, these standard sort of option pricing type theories, and, they exist, of course, right? There are economists, who win Nobel Prizes for developing them, sure, but they've basically been developed separately from the standard climate economic way of looking at the world. And sort of, in some sense, over the past 3 decades, these developments have happened in different silos. What that leaves us with as climate economists is with a very unsatisfactory view of the world, let me put it that way, or one where if you do look over to the financial economists and their methods, there's sort of this divergence. Now, when one then tries, and this is the moment where I'll share a few more of my own links, but when one tries to apply financial economic principles to climate economics, sometimes happens, what often happens is that what we think we know gets turned upside down. So what we think we know as climate economists looking at the standard view is that, right, there's sort of the expected value, the stuff we know, and then yes, there's risk on the side as well. We ought to add that. Well, when you look at a financial economic approach to climate economics, maybe some of those things we thought we knew even get turned upside down. So, for example, this optimum carbon price path, which, by the way, does not mean that the carbon tax is the only way to do this, but, right, there's a, and sorry, the kids are back with the dog, slight noise in the background. There is a sort of standard view that says you start low and you increase over time. Well, when you take risk seriously, when you make it about risk, when you make it about quantifying the risks and uncertainties, this standard view might even be turned on its head, right? It's the risk that drives, the uncertainty that drives our thinking earlier on, which means start high and ambitious and maybe even decrease over time because, well, risk and uncertainty is going down, alternatives are becoming cheaper, right? Lots and lots of factors figuring into this overall price path. But yes, it may actually change our standard view. So to answer your question, right, we don't know what the component is, what the risk component is, what the expected value is. What we do know is that the standard view, our sort of standard social cost of carbon calculations, often ignore that risk, that tail, and of course they ought not to, right? So here's sort of our broad recommendations to the Biden administration trying to make sense of climate risk and improve those social cost of carbon calculations. One of the key bits is precisely this, like, risk aversion, uncertainty, how to deal with these high impact, low probability events, tipping points. It is a major, ought to be a major component of this exercise. So in other words, treat CO2 like an asset, like a financial asset, one with negative payoffs once it's in the atmosphere, but as an asset nonetheless. And using these asset pricing methodologies sometimes turns upside down what we think we know ought to happen policy-wise, or for that matter, right, from a corporate perspective, from a financial perspective. How do you price climate risk? How do you price climate risk in a big way, part of, right, the risk you face in terms of your investments because of unmitigated climate change, and then sort of the policy risk as well, right? What if policy changes, prices CO2? How does that affect my investment decisions? Well, both ought to treat CO2 like an asset. Ought to treat this process of pricing CO2 like it is a financial decision, which, preaching to the choir here, right? This is not news to anyone, hopefully. In many ways, we ought to get on with it, right? We ought to actually be doing this. And then once you do this, last link, last 30 seconds here, everything we think we know suddenly follows this pattern. So this is, despite Jennifer's warning before that, right? So in the climatic system, thinking of it as tipping points may not be the right way. We do call it tipping points here, climatic tipping points, and then try to translate it into dollars and cents once again. And when you do that, the impact of the tipping points follows one of these tail distribution, one of these distributions with a long right tail, right? So very loosely speaking now, that's not technically the right term I'm using here, but if you look at tail events, the impact of those tail events follows yet another distribution that has a long tail, right? So a tail on top of a tail, right? It's the risk that matters. It is the uncertainty that drives the final outcome. It's all about taking climate seriously as a risk mitigation problem, as a problem of mitigating, decreasing uncertainties. And yes, right, that's where the action is. That's where the action ought to.
Okay, thanks, Gernot. And just wanted to remind people that there seems to be a lot of good information, links and materials and so on landing in the chat. There is an option if you're joining on WebEx on your desktop to save the chat. So I encourage people to do that. And we'll also try to distribute those links and materials to people after the event. I would eventually like to open it up to questions from the audience, but I do have one more question, and this ties in, Gernot, with what you were saying about, I'm sure your models are giving you very nuanced policy paths that relate to both the costs and the the costs of inaction and the costs of action that could be taken. But the IPCC has sort of a much more straightforward recommendation, and I know that the International Energy Agency has sort of run with this and come out with a report about how this could actually be implemented. The IPCC has said, I believe, that in order to meet the Paris goals, in simple terms, we need to cut global emissions in half by 2030, and then be fully carbon neutral by 2050. And a lot of institutions of various kinds have sort of latched onto that. And so we've got a lot of public and private sector entities that have committed to the idea of being carbon neutral by 2050, but fewer have talked about cutting their emissions in half by 2030. And that seems like a much tougher problem, a much heavier lift. So my question then sort of to each of you and whoever wants to begin, we can have sort of an open discussion about it. But whoever wants to kick it off, why is that an important piece of the puzzle? What happens if we miss this short-term 2030 part of the goal, and we focus more on that longer-term carbon neutral by 2050?
Well, one simple answer to that is that the slower we cut carbon emissions now, the harder it's going to be to reach that net zero by 2050. We're just making it that much harder for ourselves. The slower we get out of the box. And we're already behind the 8 ball. We should have started this 30 years ago or even earlier. And so we've got just a huge challenge ahead of us. And the longer we wait, the harder it's going to be.
Yeah. So to pile on, right? So yes, of course, right? It is all about it's not a question of what we need to do, right? We know that, right, as long as there are positive emissions, as long as we add to the atmospheric bathtub, climate risk will increase. There's no other way of putting this, right? And so it's not a question of if we need to net decarbonize, if we need to stop adding CO2 to the atmosphere. The question is when and how we do it, right? And if we don't do it by 2050, well, we'll do it by 2070 or 20 whenever, or 21 whenever. And up to that point, climate risk will increase until we finally stop adding CO2, right? So the sort of, the risk management approach to this is to say, wait, we need to figure out how to achieve the transition, how to finance it, how to do it, not if, right? And yeah, this is where, frankly, where financial tools are incredibly useful to guide us in terms of policy, and of course, vice versa, right? So, one of the links I shared, one of my co-authors, Bob Litterman, ex-top risk manager of Goldman Sachs, who, right, sort of, actually, when he tells the personal story, he tells it as if it's sort of the most natural thing, right? You apply the exact same techniques you apply as a risk manager for a financial firm to climate, and the conclusion sort of stares at you, jumps out at you, is sort of the most obvious thing you can do. There isn't really much else. So in the chat here, I see a question about, right, solar geoengineering, cloud seeding, geoengineering technologies in general. Just very briefly, largely because I do have a book out next week, I think, in the US, in the UK a month ago, right? Geoengineering, the gamble, which, it's a risk. If climate change is risky, right, the appropriate way to look at geoengineering is as a risk-risk trade-off here. There are lots and lots of good reasons to want to do a lot more research into these sets of technologies. I'm talking about solar geoengineering right now. Yes, is it a replacement for cutting CO2 emissions? No, it's not. Right? There are sort of all these reasons to believe that, yes, of course, we can, sort of quote unquote, buy time of sorts. Yes, by adding lots of additional risk to the equation. Sure. Should we be doing the research, the hard work to find out? Yes, we should. Absolutely. Does it prevent us from cutting emissions? No, it does not. Lots more to say, of course, about this overall topic, but at the end of the day, yes, the goal is clear. The question is, right, who pays for the transition? How do we achieve this transition? And yeah, what's the timeline? How do we get there? Should the EU go to minus 55% by 2030, or should it stay at minus 45% by 2030? Right? It's these sorts of questions. The how, the when, not the if.
I just want to add one point on your original question, Jim, about 2030 versus 2050 and all this. I think the science in some ways has actually gotten a little simpler on this in the last decade or so. So we used to say that even if we stop emitting carbon today, it'll still get warmer for some period of time. And we actually know that that's not really true. And what we understand now is that the total global warming we see in the long term is directly and relatively simply related to the total carbon emissions to date. So it's a budget. We're talking about finances. That's why people talk about the carbon budget. How much have we emitted? That's how much warming we're going to get. And, so exactly what trajectory do we take? One can debate, but the longer we put it off, the harder it is to do it, both technically, politically, and probably every other way. So, because then you're trying to do it more steeply and you will have emitted more before you get there. So I think, that's just useful to keep in mind as we look at these targets.
Okay, thanks. There are so many other questions I'd like to ask, but I would like to open it up for questions from the audience, and we're running a little bit short on time. So let's go ahead and do that now. If you would like to ask a question, please raise your hand. There should be an option to do that in the reactions menu at the bottom of your screen. You could also type your question in the Q&A box, which should now be open, if you prefer, but please don't use the main chat for questions. We won't be monitoring that for questions from the audience.
Well, there was a question back there in the chat that I saw asking about how the future sea ice scenarios relate to the IPCC scenarios. And that's exactly what they are. What I showed you was the model simulations for those different IPCC scenarios. So the red line, which is the one that I called the do nothing line, that is sort of our worst case scenario, or business as usual, or if you understand IPCC lingo, it would be RCP 8.5. And then the green line, which is what we're all trying to aspire to, and all of our work is aiming to try to keep us on that green line. That would be, the most aggressive scenario of reducing emissions of carbon into the atmosphere. So they are directly connected to each other.
Okay, thanks, Jennifer. That's helpful. And with your permission, maybe we'll be able to distribute your slides to the audience if you.
Absolutely.
Okay, great, thanks. There is a question in the Q&A box. What are some of the biggest levers that can be pulled in the effort to reduce carbon emissions on both a large global scale and at the individual level? So I don't know who wants to start with that. It sounds like maybe it's an economist kind of question, but. Anyone's feel?
I feel seen. Well, actually, here's the cop-out answer. Pull the highest lever you can using your comparative advantage, right? So, as concepts go, comparative advantage is a thing, right? If economics is organized common sense, then yes. This is one of the main concepts here, right? Not absolute advantage, comparative advantage. And yes, it's about pulling the highest lever. So, what could we be doing right now? Well, everything that we can to make sure that the $3.5 trillion Build Back Better reconciliation infrastructure, whatever it's called as of late, plan, in fact, includes solid climate provisions. There is a carbon tax being debated in some Senate committee as we speak. It is $15 per ton. Is that high enough? No. Is 15 better than zero? Yes. Is it more important to get started than, frankly, anything else? And is it more difficult to get from 0 to 15 than from 15 to 150? Yes, that too, right? So all of the above, right? Yes, of course, let's push for the right policies. Okay, from an individual perspective, if you will, what's the highest lever, right? So, opinions differ. One often very prominent answer given in a situation like this is vote, right? Like, it's about policy, so go out and vote. Well, yeah, sure, but, right? Frankly, here is actually, let me try this answer on you because I'm currently on an assignment to write 1,000 words by tomorrow morning for one of these rare signed Economist pieces, right? So the Economist magazine, right? It's an anonymous newspaper. and yes, they call themselves a newspaper, right? And then they ask, for these signed pieces every once in a while. My assignment is, what's the highest lever you can do on an individual basis without pulling the policy lever, without parliamentary action, right? What can one do? Okay, so again, the cop-out answer is vote, but of course that's not what they're after, right? So here's, let me try this on you. Strictly from an individual level, right? Well, what's the most impactful decision that one can do? Right? Other than, how to spend your time and how to spend, what little time we have on this planet and so on and so forth, not to wax too poetically. Well, the most significant individual decision is where to live and how. Right? And I'm not talking about, US versus Europe or something, but in some sense, right? So, New York area, let's say, do you live in the 5-bedroom colonial an hour outside the city, or do you live in the city? How do you live? How do you spend your money, right? On housing, on real estate. And frankly, and this is sort of my, my quick take here. There's 1,000 words to come on this, but for basically everything else, as an economist, we worry about optimization, right? How to find the optimal. Meanwhile, for decades by now, basically everything there is in sort of the real estate sector points to maximization, points to the maximum, right? It's the realtor's incentive to squeeze out as many square feet as they can with the money you tell them to, the budget you tell them. It's the mortgage banker, right? The banker's job to squeeze out as high a mortgage as possible with the parameters you tell them, right? It's all about maximization, like every step along the way, all the way to the divorce lawyer, literally, right? The divorce lawyer has an interest to want you to live in a bigger home because it's better for them, right? If and when that house gets sold, it's better to have a larger home. So every incentive, and then sociology, psychology, right? On Instagram, right? You show the size of your home, right? Real estate porn, right? Looking through the mansions, right? It's not about optimization, it's about maximization. And by the way, the 45-minute commute, of course, does not get streamed on Instagram Live, right? On a daily basis. If anything, that's sort of a sacrifice, right? That's a noble gesture, right? The dad sacrifices his time to allow the 15-year-old to have her own bathroom further out of the city, right? Sort of this whole process, right? Every step along the way is about more maximization as opposed to optimization. Okay, so what do you do? Well, now we are sort of in the self-sacrifice portion of this conversation, right? But of course, the question is how to turn that into, from a very economic perspective, into an optimization conversation as opposed to a, minimization, maximization, or whatever else a bit. Is that the highest level one can pull? Well, it's certainly the most consequential, right? The average person living in New York City has half the emissions or a third of the emissions than the average suburbanite, right? What does one do with that information? At what point do you say, right, it's not just the moral choice, but it's the optimal choice? It sort of gets us closer to where we need to be. It's certainly a very high lever to pull on an individual basis.
So thanks for that. And of course, you're talking about sort of voting and public policy in addition to individual action, but there's a third option in between, which is businesses and industry. How do private sector businesses behave, and what do they do? And I think people are thinking about that a lot in the financial industry. And but to some extent, the financial industry is always going to follow public policy, right? I mean, if you're going to make financial decisions, you have to think about various time horizons and various possible outcomes. But to a large extent, the risk reward trade-off that you're weighing in your decisions have more to do with what public policy is going to look like a few years down the road than it does with, you know, what the physical climate system is going to look like a few years down the road. So
Exactly.
any thoughts about that from any of the panelists? You know, sort of how we expect public policy to evolve, and it seems like I mean, we've gone in a very short time from the Green New Deal seeming like a radical idea out of left field to you know, something that looks like it potentially could be passed, and you know, this is what ties it back to extreme weather events and to the visible impacts that we're experiencing right now of climate change. You know, is that shift in public opinion to some extent related to the idea that we're seeing these impacts already, and if the impacts are going to continue to get worse, does public opinion continue to shift in that direction, which then would change the calculation in terms of what the optimal financial allocations are, right? You all of a sudden, if you think that we're going to really be on a path to decarbonize more quickly than people are assuming, then you completely change your investment profile as a result of that. So I think that sort of ties it all together in terms of looking at the physical impacts and looking at the economic policy. And any thoughts from anyone about how that all may play out in the future? I mean, are we going to continue to see more and more severe impacts that will shift public policy, and then how will public policy likely change?
Well, I think, I mean, I'm trying to restrain myself from getting too political here, but I mean, I think that in some level, public opinion has already shifted a lot. And to whatever extent that's due to visible extreme weather events that are attributed to climate change, for example, which I think is part of it, that's going to keep happening. So, you know, I think to the extent that we have a political system that's responsive and is able to prioritize that, we'll see a transition, and it's going to happen, and it's only a question of how fast. Now, there's all kinds of dysfunction in our political system. We all see that every day. And, you know, whether it responds to the public opinion on this in a way, you know, in a timely manner, or whether it takes, you know, a lot longer than it should, I don't want to try to predict, but I think we are probably already reaching the point where, you know, to whatever extent it comes from public policy in the sense of laws being passed in the United States or in other countries, or just bottom-up pressure from the media, the public, shareholders, if we're talking about corporations, you know, and so on, the transition is going to start to happen. You know, we haven't talked about this, but renewable energy is getting a lot cheaper and a lot faster, and is growing rapidly. It's still way too small a share of the energy we use, but you know, it's a real wave that's coming one way or the other. And from that and a lot of other perspectives, you know, at some point it's going to pay off to be on the right side of history. You know, when and exactly how that happens, maybe my colleagues will be braver than I to predict, but that's my take on it. I think we're there sooner than, you know, I think we're.
But to be clear, it has happened.
Realized.
Right? It has happened. So when IEA declares solar photovoltaic the cheapest form of electricity in history, you know, they are not an activist group trying to, you know, sort of play the public here, or like, it's true, right? It is the cheapest form of electricity in history. Now, you know, given sunny locations and cheap finance, so there's a crucial role, of course, that finance plays here. But right, it already is. If you were looking at the marginal gigawatt or megawatt installed, it's photovoltaic, it's solar PV, right? A tenth of the cost from a decade ago, 100th of the cost from 40 years ago, right? So in many ways, you know, it's a race between tipping points. How about that, right? There's the climatic tipping points, the sort of the, right? And then there's the societal, the economic ones. And, you know, is it enough that solar PV is the cheapest form of electricity in history? Well, no, it's not, because it's the existing energy infrastructure that still keeps polluting, right? I mean, there's still, right? It still pays to keep the coal plant operating because you're not paying for the pollution. And therefore, right, we are seeing continued pollution in the power sector despite the alternative. Now, what does it take to do that? Well, right, so it's the Asian Development Bank teaming up with, I think, Citi, BlackRock, and HSBC to create a financial program, a system to buy up existing coal plants and retire them before their lifespan, and do so, profitably. How do you do this profitably? Well, you do it by subsidies, right? Asian Development Bank providing some of the money, and HSBC, traditionally the bank, I think the largest coal financier on the planet, right? Trying to find ways to make money off the transition, given subsidies. But yeah, it's right. It's that needs to happen, and there too, of course, right? We are seeing smallish tipping points left and right in the right direction, and yeah, it's a race between the bad sort of tipping points and the good kind.
I think you might be muted, Jim. At least
I
don't
was
know.
muted.
Yeah, I was wondering if I was the only one who couldn't hear
So
him.
yeah, sorry. I was just saying we're just about out of time, but Jennifer, I did want to give you a shot at that question also. How you see things playing out in the near future, the next 5-10 years, policy-wise, and what should the financial industry expect from should they be looking for any surprises in terms of shifts in policy, in your opinion?
So, policy is really not my thing, but just getting back to the topic of subsidies, we're still subsidizing the fossil fuel industry, and I think that needs to stop right away. I think that's one of the fastest, simplest things that we could do to start to shift this story. Give that money to renewable and grid infrastructure projects, and really start to spend some money on the future rather than supporting the dirty past. And just to get back to extreme weather, kind of a final note on that, I think, there is a silver lining to all of this, really, as Adam talked about in the very, very beginning, how 2021 has already been such a unbelievable year for extreme weather all around, especially the Northern Hemisphere. I think it is waking people up. I think people are looking out their own windows and feeling it in their own pocketbooks and in their own lives, that things are just not the way they used to be. And there's just a lot of very unusual stuff going on in the atmosphere and the oceans, and people are really starting to wake up. And I think businesses are also starting to wake up to the fact that they have assets that are potentially vulnerable to some of the extreme events that we're already seeing. And they're just going to get worse, especially for the next couple of decades, no matter what we do. So we have to get ready for more extreme events in the near term, in hopes that we can stay on that green line that I showed, in which case they potentially could level off, but still at some worse level. So we have to get ready for that.
Okay, that sounds like great advice, and I think we'll have to leave it at that for today. We're out of time. But people who do have questions, if you didn't get a chance to ask, go ahead and email them to us at info@finclean.org, and we'll try to get them in front of our panelists. And as I said, we'll also try to distribute some of the materials to our audience if we can. Please join me in saying thank you to our panelists. That was a really great discussion, a lot of helpful information. We really appreciate you being here and doing this. Thanks so much. I would also like to thank our co-founder, James Padden, for a lot of work behind the scenes to make this possible. And thanks finally to everyone in our audience for being here and for your interest. So be well, and we hope to see you again soon.
Thank you.
Thanks, everybody. Thanks, Jim.